With that, I'd like to introduce our first panel chair, Professor Stephen French. Professor Steve French is a McKinney Family Professor of Sustainability, Energy and Environment, an Associate Dean for Research in the College of Architecture at the Georgia Tech Institute of Technology. He has a lot of expertise and run many projects related to risk management. Recently completed a joint project on the effects of large-scale urban form on obesity. And he's also, I'd like to mention that, a lead contributor to the EPRI Georgia Transmission Company methodology for siting overhead electric transmission lines. Dr. French holds a PhD in city and regional planning from the University of North Carolina at Chapel Hill, and is a fellow of the American Institute of Certified Planners. Please have me welcome our chair, Stephen French.
Yes, I guess I think some about, as an urban planner, I really think about modeling and simulation and looking at future scenarios of the city. And we do a lot of work on infrastructure, trying to understand how to make those, create a more sustainable city. And certainly modeling and simulation is useful for that. And I'm going to actually focus, set the table for our speakers. I'm not going to do a full presentation, but I thought I'd just focus on this concept of resilience. I do a lot of, one of the things we do is earthquake and other natural hazard modeling. So we actually use simulation to forecast what happens in a natural hazard event, and have done a number of projects along those lines. So I wanted to talk a little bit about resilience. And simple definition, it's the ability of a system to recover from some external shock. And I like 4 components of resilience that Michel Bruneau and others put together some nearly 10 years ago. And they talk about the characteristics of a system and the characteristics of a system that make it more resilient. Robustness, somebody this morning said you can't strengthen your way, you can't build a tough enough system that there's not a bigger event. So if we build for a 12-foot storm surge, there's the 14-foot that's coming 10 years down the line. If we design to the 100-year flood, well, what about the 500-year flood? If we design for a 7.0 earthquake in San Francisco, what if we get the 8.5? So robustness is one of those characteristics. Redundancy is also important. Do we have other ways? If you knock out one transmission line, does the system still function? If you knock out one water treatment plant, does the system still function? So having redundancy in the system makes it more resilient. Also, rapidity. How quickly can we marshal our resources to come back and try to bring the system back online? And resourcefulness is, do we have the equipment, the expertise, and the knowledge to actually make that recovery happen a little bit more quickly, or hopefully a lot more quickly. So here's kind of a standard model of resilience. You're going along, maybe you're operating at 97%, your system, whether it be an electric system, transportation system, is going along. There's some external shock. Could be a natural hazard, like I focus on. Could be a terrorist event. Could be could be a cyber attack. And for some reason, your system is depleted, hopefully not all the way down to zero, like we saw in parts of the New York and New Jersey area for Sandy. But you get some diminution of the functionality of your system. And then you start a climb back up, hopefully. Sometimes we don't always get back to the same, but hopefully we get back to the same level of performance. So that's kind of a stylized model. And we think about resilient systems, that this is the disruption that happens that maybe not cripples the system, but certainly impairs its functionality. And this is the recovery phase, where we actually bring the system back to full performance. Now, let's take those 4 dimensions of resilience. Robustness and redundancy can actually make the system more ability to withstand that initial shock. So we don't get as much of a effect on the system. And I should say this timeline can be in the terms of seconds or minutes if we're looking at an electric power line. This, in terms of recovery, could be years in the case of Katrina and New Orleans, and maybe at least months with Sandy, and hopefully not years. But so this time scale varies a lot with different systems and different kinds of attacks. But this is the percent functionality here, and the timeline is variable for different kinds of situations and different systems. So by employing these strategies, we can actually make the system more resilient because it doesn't have as negative an impact when it is hit with a given level of impact. And we can also work to change the slope of this recovery line so that we can actually recover more rapidly from whatever event we have. So that's the rapidity. How quickly can we marshal the facilities to do that? And is the system designed for rapid recovery? And are we resourceful? Can we actually have in place the expertise, the equipment that we can use to bring the system back? Now, of course, what we'd like to have is less disruption and quicker recovery so that we have a more resilient system. So I just wanted to sort of set the table with that sort of notion of resilience and different ways we can make a system, or maybe even a set of systems, a whole network of systems, more resilient. So I just thought I'd frame the question of this panel. How can modeling and simulation techniques help to make the city more resilient? What can we do through modeling and simulation to actually change the shape of that curve, as I was suggesting there, so that the systems come back and are more resilient? Now, as a professor, it's very hard to not try to answer the question, but I'm going to resist that and let the panelists actually take a shot at that, and hopefully the larger group as well. So our first speaker today is Maxine Agostini. He is in charge of business development and strategy for the Smart and Sustainable Cities Project at EDF. And before that, he worked again at EDF in Renewable Energy Department. Like many of our participants today, he went to École Polytechnique and majored in physics and computer sciences. But he also was an intern with both Stanford and Google, so we'll welcome him back to the Bay Area.